Hey guys, alright, in this test we're going to do the integral test and the P-series test. Basically, what the integral test is saying is that if you can write a sequence as a function of x, and that function of x is positive, continuous, and decreasing. So positive means that it's above the x-axis. Continuous means that you can draw it without picking up your pencil. And decreasing means that it's decreasing in size as you get bigger, further and further on the x-axis. So your points for A1, your point for A2, your point for A3 should be getting lower and lower as you go on. So if your function, if you wrote your sequence as a function and it's positive, continuous, and decreasing, if you found the integral of that function, which is basically area under the curve, what this test is saying is that the area under the curve of that function, if that improper integral converges, then the series is also going to converge. Similarly, if the improper integral diverges, then the series is going to diverge. So whatever the improper integral does, the series will do. Make sure that when you're using this test that you say f is positive, continuous, and decreasing. And if that's true and you prove the integral, whatever the integral does, the series will do. They converge together or they diverge together. Okay? Alright, we're going to ignore the remainder stuff for now. We'll talk about the remainder in a little bit when we get down to the example on the bottom of the page. But for now, we're going to do two examples, determine whether the following series converges or diverges. So the first thing we're going to do is we're going to rewrite this as a function of x. So my function is going to be x over x squared plus 1. Now, this function is always positive for x greater than or equal to 1. This function is positive. It's also continuous because there's no values where this function does not exist. The domain exists for all values of x. And it's also getting smaller, so it's decreasing in size. Since the function is positive, continuous, and decreasing, I can apply integral test. So I'm going to integrate from 1 to infinity the same bounds that are on my sum, and we'll integrate x over x squared plus 1. Now remember, improper integrals, we have to write that as a limit and choose any variable you want to. I'll choose a. Limit is a goes to infinity of the integral from 1 to a of x over x squared plus 1 dx. Then I'm going to have to do u sub to solve this problem. So u equals x squared plus 1. Du equals 2x dx. So that means that this x dx can cancel with that one. But this 2, I pull out a 1/2. Integral of 1 over u du. And I'm going to change my bounds now. So if I plug in 1, I get 1 squared plus 1, which is 2. And if I plug in a, I get a squared plus 1. So my bounds are now 2 to a squared plus 1. So I don't go back to x because I changed my bounds to u values. So let's evaluate this integral. The integral of 1 over u is natural log. Let's plug in the top bound. Alright, and there's my integral evaluated, and when I plug in infinity, then I have 1/2 times natural log of infinity squared plus 1 minus natural log of 2. So this equals infinity. minus 1/2 natural log of 2. Well, that is going to diverge. And so since my improper integral diverges, therefore my series will diverge by integral test. Okay? All right, let's do the next example. So we have 1 over n squared plus 1. Let's rewrite that as a function. And this function is, for x greater than or equal to 1, is always positive. It's always continuous. And it is always decreasing. So we can use integral tests for this function. So we rewrite the sequence as an integral using the same bounds as my series. And we rewrite it with a limit statement. And then we integrate 1 over x squared plus 1, which you should recognize is inverse tangent. All right, we've talked about this many times in class before, but if you plug in infinity into inverse tangent at infinity will approach pi over 2. And inverse tangent of 1 is pi over 4. So this limit will equal pi over 4. And so this integral converged to pi over 4. Therefore, our series will converge by integral test. Okay? Now, it's not going to say that it converges to pi over 4. It just says that it's going to converge. If you want to find out whether or not your series, what number your series converges to, you can't really do that with integral test. The only thing that you can do for integral test is find out the interval of where the series converges to. So the error in a series estimation, your actual series will be in between these two values, the integral from n plus 1 to infinity of f of x dx to the integral of n to infinity of f of x dx. So what this is saying is that this series, the most it will be is pi over 4. But if I wanted to find the lower bound of it, I would integrate from 2 to infinity, and whatever value I get from 2 to infinity would give me a lower bound of my error. Okay? We're going to skip this for now, and we'll come back to error in a little bit. Actually, we're going to just finish this. So what we're going to do is we're going to find the sum of 6 terms. Sorry, I had to go grab my calculator, and so I think it's better if we just finish this problem. So we're going to first find the sum of up to 6 terms, which will be plugging 1 in. So 1 over 1 to the 4th plus 1 over 2 to the 4th plus 1 over 3 to the 4th plus 1 over 4 to the 4th plus 1 over 5 to the 4th plus 1, 2, 3, 4, 5, 6. So 6 terms. And if you calculate that, you're going to get the number 1.0811. All right, well, the error in my approximation is going to be less than the integral from 1 to infinity of 1 over x to the fourth. We've already discussed that by this right here. So let's go. I don't think I can actually do it in my calculator, so let's just integrate it. Sorry, one day. So this one goes to 0 and this one goes to 1/3. Okay. So my error in my approximation would be less than or equal to 1/3.